Support for the Alan L. Edwards Psychology Lecture Series is provided by the University of Washington Alumni Association.
Good evening. My name is Sherry Mizmori. I'm professor and chair of the psychology department here at the University of Washington. And I have the distinct honor of welcoming you to the 2014 annual Edwards Public Lecture Series. And I'm pleased that you could join the psychology department tonight as we spotlight the science of decision making. Now, before I introduce this evening's lectures, what I'd like to do is just give you a little bit of background that will tell you about how these lectures came about. Now, this truly exciting annual lecture series is the result of a generous donation by the family of Professor Alan Edwards, who was a faculty in our department for 50 years, from 1944 until 1994. And his family established this endowment, this gift, that allows us to bring these public lectures to you free of charge, basically indefinitely. So that's really a great gift and very generous of the family. Now, Dr. Edwards was an outstanding teacher, researcher, and writer who is credited with changing the way that modern psychological research is conducted by introducing our current modern statistical methods. In fact, his statistical books remain the gold standards for many kinds of psychological research. Now, tonight, our speakers will explain the inner workings of how we make difficult decisions. And again, I want to thank the Edwards family for making this possible. Now, my first speaker is Professor Susan Joslyn, and it gives me great pleasure to introduce Susan. Dr. Joslyn received her bachelor's, master's, and Ph.D. from the psychology department here at the University of Washington. She received her Ph.D. in 1995. From 95 until 2010, Dr. Joslyn was a lecturer and then senior lecturer in our department, where I must say she received some of the highest student ratings. Now, during that time, Dr. Joslyn also continued her research on memory, including repressed memories and decision making. Since 2002, she's been continuously funded by federal agencies such as the Office of Naval Research and the National Science Foundation. She became assistant professor in our department in 2010, and this was quickly followed by promotion to associate professor with tenure in 2013. Now, Dr. Joslyn is a leading expert in decision making, especially decisions made under various conditions of uncertainty. Now, as you'll hear about tonight, her work touches directly on many decisions and issues that we concern ourselves with in everyday life, such as the interpretation of weather predictions. In fact, her expertise is sought after by both professional and civic groups, including the Boater Information System. It's a group that helps Puget Sound boaters access and evaluate weather conditions. Her accomplishments are published in the range of scientific journals, and her most recent work received an American Psychological Association Nickerson Award for the 2012 Best Paper published in the Journal of Experimental Psychology. And so with that, I'd like to ask you to join me in welcoming Dr. Susan Joslyn.
Okay, thank you, Sherry, and thank you, everybody, for coming out tonight on such a soggy evening. What we're going to be talking about tonight is decision-making under uncertainty. So I'm going to start by giving you a kind of simple example, because this is something that we all do all the time, whether or not we're aware of it. And this is a decision in which a person is trying to decide whether or not to bring an umbrella to work. So imagine you are this person trying to decide whether or not you want to bring an umbrella to work today. Let's imagine that it's not raining right now. So what you have to base your decision on is something that is currently uncertain whether or not it will rain. And when that happens, whatever you choose, so let's say you choose to bring your umbrella, there are two things that could possibly happen. So if you choose to bring your umbrella and it rains, you will stay dry, and that's a good thing. If you choose to bring your umbrella and there's no rain, you have to carry it around all day. You might leave it under your chair somewhere, and that is potentially a bad thing. If you leave your umbrella at home and it rains, then you'd get wet, and that's definitely a bad thing. But if you leave your umbrella at home and there's no rain, then you don't have to carry it around all day, and that's a good thing. So in situations like this, where you're basing your decision on something that's currently uncertain, what you'd really like to know, in this case in particular, is what are the chances it's going to rain, right? Is it going to be a 10% chance, or is it going to be an 80% chance? And that's what I'll be referring to as uncertainty information. Information about the likelihood of some key event for a decision that you're making. That was a really simple example, but we all make fairly important decisions that have this same structure. So for instance, decisions about medical treatment options. Should you have surgery? Decisions about what to do with your retirement savings. Should you put them in stocks or bonds? Decisions about what to do in the face of severe weather. And that'll be one of the primary topics for my talk tonight. So in a lot of these situations, there is good information about the uncertainty, so the chance of blood clots with surgery, for instance, or the chance of high winds. But experts who are providing this information to us often opt to keep it simple. And in particular, they don't want to burden us with numerical expressions. So they often give us categorical expressions of uncertainty. So for example, when we're facing surgery, they tell us there's a small chance of infection, blood clots, or stroke. A financial planner will ask us, is our tolerance for risk high, medium, or low? The National Weather Service has a similar categorical system for describing destructive weather events such as floods and high winds here in the Northwest, or tornadoes or hurricanes in other parts of the country. It's the watch and warning system. And so if you go on their website, you can find these definitions. So a watch is when conditions are favorable for a weather event that may pose a risk to life and property. They're issued up to 48 hours in advance, although there's currently a flood watch for Western Washington, not in King County, but in many of the other counties. And it indicates a forecaster confidence of around 50%. An advisory is a weather event that's imminent or occurring and may lead to nuisance conditions with forecaster confidence of 80%. And a warning is similar to an advisory, except it's for an event that would pose a risk to life and property, again with forecaster confidence of about 80%. So when these are issued, however, they don't give you all these definitions. They just tell you there's a watch, an advisory, or warning, and then they describe the event. And this works pretty well in most situations, but there are some notable problems. A recent one was a rare winter storm in the city of Atlanta, Georgia. On Tuesday, January 28th, snow began falling about midday, and about 1 million motorists tried to leave the city at exactly the same time. The roadways iced over, turning them into icy parking lots riddled with accidents, and thousands of people were trapped in their cars, some up to 18 and 20 hours, without food, without water, many of them without heat once their gas ran out. Some of them simply walked away and camped out wherever they could in supermarket aisles, hardware stores, and churches, hotel lobbies. Approximately 2,000 school children spent the night sheltering in place in buses, police stations, and classrooms. So why did this happen? Well, according to Governor Nathan Deal in a press conference that night, it was due to bad forecasts. It was the forecaster's mistake. He said the forecast was for a mild dusting, very small accumulation, if any, and the majority of effects would be south of here. He went on to say that when making this decision, he was concerned about being accused of crying wolf if no snowstorm happened, or lost productivity in the city. So he said, if we close the city of Atlanta and our interstate system based on maybes, then we'd not be a very productive government or city. And then he reiterated, we can't do it based on maybes. So he clearly doesn't think this snowstorm is very likely. What about the weather forecasts? Let's look at the National Weather Forecast watches and advisories for this event. The first one was well in advance, about 45 hours before snow began falling on Tuesday. It was Sunday at 3:12 p.m. There was a winter storm watch for the South Atlanta area. By 4:53 a.m. on Monday morning, again, the day before this happened, it was upgraded, it was for the entire Atlanta area. By 3:22 p.m., they added in a potential for 2 inches of snow and a half an inch of sleet from Atlanta to Athens. By 9:36 p.m. on Monday, it had been upgraded to an advisory. Remember, this means 80% forecaster confidence. By 3:39 on Tuesday morning, still with plenty of time to close schools and government offices, it was upgraded to a winter storm warning. Reduced visibility, significant amounts of snow, travel is dangerous, travel only in an emergency. And yet, Tuesday morning, Atlanta schools and government agencies remained open. Business as usual. By about 10 a.m., Governor Deal must have been getting nervous because he declared a liberal leave day, which means that you can take the day off if you have vacation. 12:30 p.m., the snow started falling. 1 p.m., that's when the million motorists entered the roadways. And by 5:28 p.m., there was a state of emergency. Many people didn't get home until well into the next day. So again, why did this happen? The forecasts were good, the information was available, but it didn't seem to influence decision makers. Now, there are a lot of things that led to this fiasco in Atlanta, including lack of equipment and decentralized decision structure. But you have to wonder if at least one of those things isn't communication, and in particular, the communication of the likelihood of the event. And that's what I'm going to be talking about tonight, a research program that investigates communicating uncertainty in weather forecasts. And this is something that I became interested in over a decade ago when I became part of an interdisciplinary collaboration here at the University of Washington between statisticians, atmospheric scientists, and psychologists. And the main goal of this project was to bring more uncertainty information to general public end users of weather forecasts. So for many decades now, we have had one kind of uncertainty information. It's the probability of precipitation, such as a 30% chance of rain. But what we wanted to do with this project was bring more of that information to other kinds of forecasts, like a nighttime low temperature. So at the time, and still today pretty much, what you get is a single value. So nighttime low temperature will be 32 degrees, implying that it's going to get colder and colder till it reaches 32 degrees, and then it'll start getting warmer again, and that's exactly what's going to happen. And so for that reason, I'm going to refer to this as a deterministic forecast. But let's say that you are a wine grape grower in eastern Washington, and your crop has reached its bud stage. So freezing could devastate this entire crop, costing you tens of thousands, maybe hundreds of thousands of dollars. So you're going to want to engage in crop protection procedures, and they have a bunch of things they can do. There's smoke pots and cover it with plastic and stuff like that. If there's as low as maybe even a 20% chance of freezing. So you're somebody who needs to know the probability of freezing. So in this situation, the forecaster probably knew that there was some uncertainty in that forecast and probably selected some probability beyond which to issue a forecast that said it was going to freeze. So maybe when it was 50% or 80% chance of freezing, then they issued a deterministic forecast saying that it would freeze. But this is a situation where the person's livelihood depends on the weather. Maybe that's a special interest group. Maybe not everybody needs to know all of this information. So that was one of the first questions that we wanted to ask with this project. Does the general public need explicit uncertainty information? Then we wanted to know, can people actually understand it? So it could be that they need this information, but that they wouldn't understand it if they had it. And then finally, we wanted to know, does uncertainty information improve people's decisions? So it could be that they need the information, they understand it, but it could not impact decisions one way or another. So that's what I'm going to talk about tonight. I'm going to talk about a series of studies that address these three questions. So beginning with, does the general public need uncertainty information? This was a survey study that we did of about 1,300 residents of the Pacific Northwest, and we asked them a bunch of questions, and one of the questions was, at what probability would you take precautionary action for, and then we described some serious event. And so they filled this in with a single probability. So this is one of those questions. At what probability would you begin preparing for a 100-degree temperature? So what I'm showing you on this graph is the proportion of people on the vertical axis selecting various probabilities on the horizontal axis. And the thing to notice about it is that there are some people who would begin preparing at 10% chance, and some people who would wait until it was actually happening, and everywhere in between. So here's another one. This is for 20-degree nighttime low temperature. So remember, this is in the Pacific Northwest, so that's very cold for us. And same pattern. There are some people who would begin at 10%, some people who would wait till 100%, and everything in between. This is extreme rain, similar pattern. Snow, similar pattern. High winds, similar pattern. And now I'm putting it all back together again. This is why it was 3D all along, because I wanted to be able to do this. And the thing to notice about this is that there is not a single event for which there is a single probability that more than about 25% of people would begin taking precautionary action at that probability. In other words, it's not a one-size-fits-all kind of thing. So if the forecaster is selecting a probability, then whatever probability he's selecting, he's not helping even the majority of people for the events that we tested here. The other thing that we asked them about was about their expectations when given deterministic forecasts. So for instance, a nighttime low temperature in December of 32 degrees. Participants expected it to be anywhere between 28 and 36 degrees. In other words, they didn't expect it to be exactly 32 degrees. This was true of 99.99% of participants. That sounds like a joke proportion, but that's actually true. Expected a range of outcomes. And for forecasts further into the future, so a forecast of a week from now as opposed to a forecast for tomorrow, they expected a wider range indicating more uncertainty, which turns out to be true. Forecasts further into the future are more uncertain. For warning forecasts, they expected a high false alarm rate, and this is also true. For rare extreme forecasts, daytime high of 100 degrees, remember this is the Pacific Northwest, it hardly ever happens here. People thought it would be much cooler. In other words, all the way down to 90 degrees, but only up to 102 degrees. So they expected it to verify more toward normal temperatures. This turns out to be not true. And it's not true because forecasters also know that this is a very rare event. They're reluctant to make these kinds of forecasts. So if you get a forecast like this, it's actually more likely to be more extreme, in other words, warmer in this case. So let's take what we've learned from this study back to my question about what happened in Atlanta. Decision makers know that weather forecasts are uncertain. So when they're given a deterministic forecast or a warning that doesn't specify the uncertainty, they're perfectly willing and capable of estimating that likelihood themselves. They know that there's a high false alarm rate for warnings. They think they're wrong, but they think that extreme forecasts are exaggerated, and snow Atlanta is definitely an extreme forecast. So they may actually underestimate the likelihood of the event. So providing people with numeric uncertainty expressions might help in these kinds of situations. So this suggests that people understand that there's uncertainty in forecasts, but can they understand uncertainty forecasts? And that's the next question that I'm going to ask. So in this study, we asked a question about the probability of wind speeds over 20 knots. This was selected because it's the minimum wind speed for a small craft advisory here in the Pacific Northwest. It's just under gale force winds. So the first thing that you have to think about when giving people information about a threshold value like this is whether to tell them about the chance of wind speeds less than 20 knots or the chance of wind speeds greater than 20 knots. And that was the specific question that this study asked. So there were two phrases, 90% chance the wind speed will be less than 20 knots and 10% chance the wind speeds will be greater than 20 knots. And half of participants got the first phrase and the other half of participants got the second phrase. And they were all asked to decide about whether to post a high wind advisory for boater safety. So the thing to notice about these two phrases is that they are describing what is virtually the same situation, a situation in which high winds are not very likely. And yet, the first phrase was very confusing to people. In fact, a lot of people thought it meant the opposite to what it actually meant, whereas the second one was very easy to understand. So based on this, it seems like the 10% chance greater phrase is better. But then we ran another study, and in this study, I'm calling it 2A because it's really similar to study 2. Participants were asked to decide about whether they wanted to post a freeze warning. So the two phrases that were tested in this one are similar, but they're about temperature and 32 degrees. So the first one is 90% chance the temperature will be less than 32 degrees. The other one is there's a 10% chance the temperature will be greater than 32 degrees. And exactly the opposite thing happened. The first phrase was easy for people to understand, and the second phrase was confusing. In fact, many people thought it meant the opposite to what it really meant. So we concluded from this that the best phrase depends on the decision. If the decision concerns temperatures less than 32 degrees, then the percent chance less than phrase is better. If the decision concerns winds greater than 20 knots, then the percent chance greater phrase is better. We think that what happens when there's a mismatch between the decision that the person is trying to make and the forecast is that it increases mental workload. So for example, if a person is trying to decide whether wind speeds will exceed 20 knots, then they focus in on that range of wind speeds above 20 knots, and they're expecting to hear something about that range of wind speeds. If the forecast then describes the exact opposite range of wind speeds, that's very confusing to them. And we think that what happens is that they have to translate that less than phrase into a greater than phrase, subtracting 90% from 100% to get 10%, until they have a phrase that matches their expectations, and all of that increases processing load, increases the chance that they'll make an error. Maybe they'll make a subtraction error. Maybe they'll forget to change less than to greater than. And all of this contributes to potential misunderstanding. Okay, so the weird thing is that after I ran this study and decided what it meant, it happened to me. I'd gone to the financial planner to find out if I was going to have enough money in retirement. And the financial planner asked me, how much do I make? How much do I save? When do I want to retire? And then he showed me a complicated graph, and I looked at it carefully and figured out what I thought it meant, and I realized with horror it was telling me I only had a 10% chance. And I started to freak out until he explained to me it was a 10% chance that I would not have enough money in retirement. I didn't see it coming. This is after I ran this study. So what I hope this suggests is what a powerful effect this is, rather than other possible interpretations. And so the bottom line here is the uncertainty expression should match users' expectations. And I believe that's on the onus of the forecaster to figure out what those expectations are and make sure that the forecast expression matches them. So back to my original question, can people understand uncertainty information? I think they can, as long as they're expressed in a way that matches their expectations. We now have a number of studies using a number of different forecast expressions that show pretty much the same thing. But just because people can understand it doesn't necessarily mean that it will improve their decisions. And when we started this project many years ago, there was good reason to think that it might not improve their decisions, because there was a large body of research in psychology and behavioral economics that suggested that people make very poor decisions with uncertainty. I'm calling this traditional decision research. It showed that people make all sorts of errors. They incur too much risk in some situations, too little in others. They're influenced by all sorts of irrelevant information without taking all of the relevant information into account. But traditional decision research asked a specific question. It asked, do people make rational decisions under uncertainty? So the comparison for these studies is between human decisions and standards of rational choice. Our question was slightly different. We wanted to know, do people make better decisions with uncertainty? So the critical comparison here is between human decisions with uncertainty information and human decisions without it, with deterministic forecasts. And that's what the question was for study 3 that I'll be talking about. This used a simulated road maintenance task, so we brought people into the laboratory and they did this road maintenance task. What they were supposed to decide was whether or not to apply salt brine to the roads to prevent icing. It had to be applied before freezing temperatures occurred, so it was based on a temperature forecast. This is a simplification of the actual task. Many other factors are taken into account when people actually make these decisions, but in the lab-based version of it, it was based only on nighttime low temperature. So here's the experimental procedure. Participants got a monthly budget of $36,000. The cost of treating the roads for 1 day was $1,000. The penalty they got if they failed to treat the roads and freezing temperatures were observed was $6,000, and this was explained as a compensation to the city that they were working for the disrupted morning commute. Each day they got a temperature forecast for the following night, and they got feedback. After every decision they made, we told them what really happened. These were based on real forecasts and observations from Eastern Washington, so they don't match up exactly. Sometimes there's a forecast that doesn't, often there's a forecast that doesn't exactly match the observation. And participants did this for 2 simulated months, so 60 trials. And finally, we took a trust in the forecast rating at the end of each month. When they were done, we gave them a cash reward. We gave them it's commensurate with their ending budget. We gave them approximately $1 per virtual $1,000 they had in their budget. And we think that it's important to actually give people payment for these tasks because we think they try harder when they know that it's a meaningful decision. So you'll probably notice that this decision has a similar structure to the one that I started with. You have to decide whether you want to salt the roads or not salt the roads. If you salt the roads and it freezes, you will have avoided that penalty. If you salt the roads and it doesn't freeze, you may think of yourself as having wasted $1,000. If you don't salt the road and it freezes, you get a $6,000 penalty. That's a very bad thing. If you don't salt the roads and there's no freeze, you might think of yourself as having saved $1,000. So here's what an individual trial looks like. This is the first day of the first month. They get the expected nighttime low temperature. In this trial, it's 35 degrees. Then we ask them, do you want to salt? And they have to press one of these 2 buttons. Their budget is always shown in the lower left-hand corner there. So the person makes a decision, and then we tell them what happened. So notice that forecast was for 35 degrees, but it actually reached freezing temperatures, 32 degrees. This person salted. That was a good thing. And you can tell because their budget is now only $35,000. So in this experiment, there were 2 groups of subjects. One group got the deterministic forecast. That's the one I've been illustrating. So nighttime low temperature is 35 degrees. The other group also got the probability of freezing. So expected nighttime low temperature is 35 degrees. There's a 20% chance that the temperature will be less than or equal to freezing. So the question for this experiment is, who wins? Which group wins? Which group ends with a higher ending budget? Which forecast is better? And it was the one with the probability of freezing. This group had the highest ending budget on average. They also had the greatest trust in the forecast. This could have gone either way. If you added the uncertainty, it might have made people trust the forecast less. But we think that because people already know that forecasts have uncertainty in them, if you make that explicit in the forecast, then they trust it more. We wanted to know how it helped. So we plotted the proportion salting on the vertical axis there over the probability of freezing on the horizontal axis. And I have these arranged from lowest probability to highest probability, but in the actual simulation, they were all mixed up. The people with the probability of freezing are in the pink line. I've labeled that the uncertainty group. The people who only have the nighttime low temperature in the white line, the deterministic group. And the thing to notice about this is that the people who have the uncertainty information salt more when freezing is likely, and they salt less when freezing is unlikely. In other words, they're better able to differentiate these two situations. So this is a decision for which there is an economically rational strategy, which is to compare the cost of treating the roads to the potential penalty weighted by the probability of freezing. This is referred to as the expected value. And when the probability of freezing is exactly 16.67%, then the cost of treating the roads and the expected value are exactly the same. That's the break-even point. And so that yields the rule that you should salt whenever the probability of freezing is greater than or equal to 17%. We only had whole number probabilities in this experiment. So you should salt when the expected penalty is greater than the cost of salting. So now I've added this line to the graph that I showed you before. It's the orange line. So you shouldn't salt at all below 17%, and then you should salt all the time after 17%. And notice that neither group does this, nor did any of the individual subjects, but the people who had the uncertainty information in the pink line are much closer to this. The biggest error overall among both groups, however, was what I'll refer to as a risk-seeking error. They didn't always salt when it was appropriate to do so. A more general definition of this is preferring to take a chance that nothing serious will happen to taking precautionary action. We were kind of glad that we got this error in the lab. We think it's an interesting error, and we think it's also a potential explanation for noncompliance with weather warnings, such as the decision makers in the Atlanta situation. So remember that Governor Deal said that they were worried about being accused of sounding a false alarm and the lost productivity. So he was saying essentially that he would prefer to take a risk that there would be a snowstorm to taking precautionary action and losing productivity. But we also think it's a potential explanation for other kinds of noncompliance with weather warnings, such as tornadoes. Particularly alarming was the 2011 tornado season. There were 553 confirmed deaths. It was the worst tornado season in US history. And the weird thing was the forecasts were good, really good. So in years up to that, the average lead time the forecast gave you, that's the time between when the warning is sounded and the tornado actually hits, was about 13 minutes. That year, it was 24 minutes. So plenty of time to seek protection. So people began to wonder if the problem wasn't with compliance. There's an interesting analysis of the 2008-2010 tornado season that speaks to this issue. What it showed was that people within the warning polygon, that's the orange shape in the middle of the map I'm showing you up there, were no more likely to seek protection than people outside the warning polygon in the same county, about 40% of each group. In other words, 60% noncompliance. Similar noncompliance rates with, or compliance rates with hurricane evacuation, between 40 and 60%. It happened again with Superstorm Sandy. Zone A under mandatory evacuation, a very low-lying area, very vulnerable to storm surge. Less than 50% of residents evacuated and 100 people died. So this is a similarity between this simple road salt task that we test in the laboratory and these real-life situations. People tend to make these risk-seeking errors. So we wondered, with respect to the road salt task, would it help if we told them exactly what to do? And we thought this would be more like the real situation, because in real situations, you're told to evacuate or you're told to seek cover. So we added a condition in which subjects had advice that was given to them by what we described as a decision support aid. It was an advanced weather modeling computer system, incorporates the most recent weather forecasts, uncertainty involved, costs associated with salting and not salting, and provides a decision recommendation. What it actually did was told them to salt using that 17% rule. So every time the probability of freezing was 17% or greater, it told them to salt. Otherwise, it didn't tell them to. It told them not to salt. Unfortunately, it didn't help. So I've added that line now to the graph I've been showing you all along. It's the white dotted line. It's kind of hard to see because it lines up almost perfectly with the deterministic forecast. In other words, it's as though they don't even have the information. And in fact, participants ignored it, and by the third trial, on average, they made a decision that contradicted the advice. So we tried explaining expected value calculations to them. That didn't help. We thought, okay, it's the math. We'll just give them the spirit of it. We'll tell them that it'll help you in the long run. So it may seem like you're spending a lot of money for nothing, but really it's going to help you in the long run. That didn't help. So then we began to wonder if it didn't have to do with the false alarms. So 64% of the time that salting was advised, the temperatures were actually greater than 32 degrees. It may have felt like throwing away money to people. On the other hand, there are a lot of false alarms with weather warnings as well, between 60 and 90% false alarms for tornadoes and hurricanes. And that's because, of course, a forecaster doesn't want to miss a hurricane or a tornado, so they'd prefer to have a false alarm than a miss. But what we're worried about in this situation is something called a cry-wolf effect. It means exactly what you think it does, that people will stop responding if there are too many false alarms. And there was some survey research that spoke to this issue where people would go in after a hurricane or a tornado and interview people. And some of that research suggests that there is a cry-wolf effect. Others suggest there isn't a cry-wolf effect. So it's kind of mixed evidence. But with survey evidence like that, there are a lot of uncontrolled variables, the person's prior experience, what their current situation is. So we thought this was also something that we ought to test in a controlled laboratory situation. So we did it using that road salt task again. So this study asks, do false alarms matter to the road salt task? So what we did was that we raised the threshold, the probability threshold for recommendation to salt slightly, which lowered the false alarm rate slightly. And we thought this might increase compliance. So in this table, what I'm showing you is in the left-hand column is the threshold for salting. So the first one I've entered here is the economically optimal threshold for salting, the one you ought to use. And this yields about 64% false alarms. And a mean compliance rate of about 69%. Compliance here means when the person salted when the advice told them to salt, and when the person didn't salt when the advice told them not to salt. So it's both of those things. So then we raised the threshold slightly. This lowered the false alarm rate slightly, but it didn't help much with compliance. In fact, not even statistically significant. So just for good measure, we did the opposite. We lowered the threshold. This increased the false alarms, and this did matter. It made things much worse. So there's your cry-wolf effect. There is a cry-wolf effect. Unfortunately, decreasing false alarms does not help significantly. So that was pretty discouraging. But we tried one more thing. We tried adding in the probability of freezing. So this is another condition in which people have the nighttime low temperature, they have the probability of freezing, and they have the advice telling them when to salt using the 17% rule. And this was the very best of all. It raised compliance up to 76%. This is significantly different. And the important thing to notice here is the false alarm rate is exactly the same. It just seems that people trust the advice more despite all the false alarms if you also explain the uncertainty to them. So this condition had the highest compliance. it had the highest ending budget, and it had the highest trust in the forecast. So we think the best forecast is the one that has all of the information. It tells the single value forecast, nighttime low temperature, probability of freezing, and gives people the economically optimal advice. We think that when people have all the information, then they trust the advice. So now I've added that condition onto the graph I've been showing you all along. It's the pink dotted line, and you can see that people do better in this condition. We were still a little worried, though, about that range right above the 17% threshold. In that range, regardless of the condition, people are only salting about 50% of the time. And the reason that we were worried about that is that there are some real-life situations in which it's appropriate to take action at fairly low probabilities. So for instance, Hurricane Ike, which hit the Texas Gulf Coast in September of 2008, when mandatory evacuation was called for the city of Galveston, shown here on the map, it was 2 days before the event. So for a heavy populated area like this, you have to begin evacuating several days before in order to get everybody out. And at that point, the chance of hurricane force winds at any given location is fairly small. They know it's going to hit the Gulf Coast, they just don't know exactly where. And for Galveston, it was only about 18%. So this is very similar to the probability threshold with our road salt task. So this is another similarity. So we decided to try another expression of uncertainty. This is an odds ratio. You may have heard about it in terms of some medical risks. So for instance, the odds of lung cancer increase with smoking. It's 6 times more likely for smokers than non-smokers to get lung cancer. It's actually only 1% chance of lung cancer among smokers, but it's a whole lot scarier when it's expressed as an odds ratio. So we wondered if this might work with weather forecasts. So in the weather forecast situation, it would be the odds of severe weather on a particular day compared to climatological odds. So for instance, the odds of sub-zero temperatures tonight are 10 times greater than on a typical March night. So we did this again using the road salt task. We added an option for what we referred to as special salt. It was to be used when the temperatures were anticipated to go below 0 degrees. There's actually something like this, but I don't think it's called special salt. So now there are 3 alternatives. You can choose regular salt, you can choose special salt, or you can not salt at all. The cost of special salt is $2,000, so it's twice the cost of regular salt. But the penalty is $12,000, so it's twice the penalty of regular salt. So what that means is that you should apply special salt whenever the probability of sub-zero temperatures is 17% or greater. So it has the very same threshold as the regular salt did. So people have the expected nighttime low temperature, they have the odds ratio, and then they have to make this decision between 3 different alternatives. So we wanted to simulate a very rare event, and this is actually fairly rare in the Pacific Northwest. So that in this simulation, there were no actual temperatures 0 degrees or less. But it got very close on day 22. And how close it got was manipulated between participants. So participants got, compared to a typical winter night, the odds are, and then some of them got 3.5 times greater, that the temperature will be less than or equal to 0 degrees. Some got 6 times greater, some got 9.5 times greater, and some got 13.5 times greater. And the reason we selected these values was that when you translate them back into probabilities, they are that range of probabilities in which only about 50% of people salted in the previous task. And now 84% are salting in that very same range. So on the vertical axis is the proportion of people salting, and the probabilities are on the horizontal axis, and notice that quite a few more people are salting. The thing is that they're also salting more below the threshold also. So this is where about 10% of people were salting before. Now 41% of people are salting. So it isn't that they're making better decisions. They're not better able to discriminate these two situations. They're just being more cautious. But for some kinds of rare extreme events, this might be the way to go. So I started out by asking whether people need uncertainty information. And we think that what this research suggests is that people do need explicit, relevant, and understandable uncertainty information to make informed decisions that are tailored to their own needs. We also think that people can understand uncertainty information. I don't mean that I think that they could pass a college test on probability theory or expected value. I mean that they understand it just enough to be able to make better decisions. And again, I don't mean decisions that are economically optimal decisions, but rather decisions that are better than if they didn't have the information. And we think this is partly because it's better information than they can estimate all on their own, but partly because it inspires greater trust in the forecast. So that's pretty much all I have to say, except to thank my collaborators and my lab group. These are my lab members, undergraduate research assistants from this year. I took them all out to breakfast recently, and this is evidence for how much undergraduates can eat at one sitting. But a number of undergraduates over the years have participated in this research. Thank you.